Greetings everyone, myself Utkarsh Yadav and here is my friend Ankit beside me. Today we are going to solve the external flow problem of flow past a two-dimensional elliptical body. Let's start with our model description. So the external flow problem of a flow past a two-dimensional elliptical body refers to the analysis of fluid flow around an elliptical shaped object in two dimensions. This type of problem is commonly encountered in fluid dynamics and aerodynamics, and it has applications in various engineering fields such as aerospace and automotive design. Now, coming to the governing differential equations of our fluid flow problem. First one is continuity equation. It expresses the mass conservation within a fluid system. For incompressible flow, the continuity equation states that the divergence of velocity vector is equal to 0. We can further simplify it as del u upon del x plus del v upon del y is equal to 0, where u and v are the velocities in x and y directions respectively. The second one is Navier-Stokes equation, which is given by, for x direction, it is del u upon del t plus u del u upon del x plus v del u upon del y is equal to minus 1 upon rho del p upon del x plus nu del 2u upon del x2 plus del 2u upon del y2. And for y direction, it is del v upon del t plus del v upon del x plus v del v upon del y is equal to minus 1 upon rho del p upon del y plus nu del 2v upon del x2 plus del 2v upon del y2, where rho is density, p is pressure, and nu is kinematic viscosity. These equations, when solved together, provide a detailed understanding of fluid motion in an incompressible flow. We are using simple algorithm for solving the problem. Simple stands for semi-implicit method for pressure-linked equation. According to the simple algorithm, the discretized form of Navier-Stokes equation is given by, for x direction, u at n plus 1 at time and I plus 1 by 2 comma j minus u I plus 1 by 2 comma j at n at time into delta x into delta y upon delta t plus sigma f at nth time and u at n plus 1 at time f is equal to minus pe upon pp at n plus 1 at time delta y upon rho plus sigma f and f at n plus 1 at time f, and in y direction it is given by v at n plus 1 at time I plus 1 by 2 comma j minus v at n at time I plus 1 comma j into delta x into delta y upon delta t plus sigma f at n at time and v at n plus 1 at time f is equal to minus pn upon pp at n plus 1 at time delta x upon rho plus sigma f and f at n plus 1 at time f, and the continuity equation sigma f n plus 1 is equal to 0. We are using mass flux at nth iteration instead of n plus 1th iteration as it results in linearization of non-linear convective term, decoupling of u and v equation, and it helps to fix the direction of upwind. Now these are the boundary conditions to solve the problem. The first one is the constant inlet velocity, which is u naught, and the second one is the horizontal velocity is 0 at the leading edge of the geometry.
So for simulation we are using Ansys Fluent. So I'm just opening the workbench. It will take some time to open as it is very heavy software.
And it is the student version of Ansys Fluent.
Now Ansys is open. So we first open Fluent Flow. Just double click on it, and from here we can change the project name. I am giving just 2D flow.
Now first we will create the geometry of our object.
To create the geometry, just right click on geometry and select the new design model geometry. Once it is open, we can make the geometry as we want. For our case, we will make the geometry of fluid inside a rectangular plate. Or
Like we need to define a domain where our fluid is flowing, so we are defining it in rectangular shape.
so first check the units in which we want to make the geometry. I am using millimeter. Select XY plane, select normal. After that, go to sketching option and make a rectangle. Specify the dimensions. Let this be 50 mm and this one equals to 150 mm. And to specify the vertical dimension, let this one also 50 mm. And for symmetry, let this one also 50 mm. So we have defined the our fluid domain, but as we want to study the simulation of flow over elliptical body, so we have to make the elliptical body also. So go to draw and select ellipse option, select the center, select the major axis, select the minor axis.
Now we will give the dimension of minor and major axis for our ellipse.
So select horizontal to give the horizontal dimensions. Let it be 25 mm. And let the vertical,
the minor axis will be almost of 10 mm.
So to make the body geometry in 2D, we will go to concept and select surface from sketches. Now select the geometry and apply here, then generate. Here our geometry is ready. Now we will mesh it. Go to workbench, update the geometry.
You also need to check for fluid. It was in solid.
Yeah. Just here, from here, check the surface body whether it is, by default it as solid, so here it is shown solid. Select on fluid, go to workbench,
As we were working for fluid, so we need to make it in fluid.
Just double click on mesh to mesh the geometry. It is taking time.
Basically, in mesh, we need to make it finer where our elliptical body is there. So we need to make it more fine outside our elliptical body, and we can make it a bit coarse, like the distance far from our elliptical body.
Now our meshing window is open. So again, please check whether the surface geometry is solid or liquid. Here it is shown fluid only, and now we can generate the mesh. By default, it will generate a random size. To show you, we can just generate the mesh. You can see that mesh is not as perfect as we want. So here it is shown that element size by default it is 0, so we will make it 0.001 and generate. It will take time as per your mesh size. If the mesh sizes are mesh meshing is very fine, it will take more time.
We need to make the mesh more fine to study the fluid properties more accurately near our elliptical surface.
You can see that our mesh is nice, but here also it is not that too good. So again, go to mesh, go to sizing option. From here select the edge option. To select this, from element size, you can give the element size also. I am giving here number of division, and let it be 400 and generate the mesh. Now it will make the mesh finer near this elliptical body. Now our mesh is ready. You can see that mesh is more finer near the elliptical body. So we can set up the simulation. Before going for simulation, let's give the name to the boundaries. So select the edge here, right click on, to give the name to the boundary, just left click on it and just right click on it, create name selection. Right here, wall, create name selection, wall, inlet here, and outlet here. We can give the name to the geometry also. So now our mesh is finally ready. We can go for the setup option. Just update the mesh.
As we already made the geometry and we already make our mesh, now we will do the setup of our mesh and geometry. For that we need to just double click on our setup.
Select the double precision for more precise values of the results. And here you can see that Ansys all already selected 2D. If our dimension geometry were 3D, so it will automatically take it 3D. So just restart.
Now here we can see our created mesh, our geometry and our inlet as blue and our outlet as red.
Just click on the transient for transient study. And before setuping the thing, click on the check mesh. It will check whether our mesh is right or wrong. If our minimum volume is coming out to negative, then it will be wrong, and if our minimum volume is positive, then our mesh is correct. Here you can see that our minimum volume is positive only, so we can proceed with our simulation. Go to models, select viscous SST From here, select laminar flow,
As
click
we are
OK,
dealing with the laminar flow here in our, like in our, where our geometry is.
go to materials.
Here we can also choose any other material, but we are dealing with the air.
For choosing the new, go to create. From here we can go to and select the material which we want for study. Let's say if you want to go with water liquid, select water liquid, select copy. You can see that water liquid is also added in our materials. Close, close. But till now we haven't assigned the fluid to our mass or geometry. So go to cell zone conditions, select surface body, edit.
Now here we will define air as our fluid material that is flowing inside this our geometry.
So if you want to select the water liquid, you can select from here, but we are going with air only. So click on apply, close. Now with boundary conditions, we will be defining only boundary condition at inlet. Let's say velocity is 0.3 meter per second. If you want to change the specification of velocity, you can change from here. For now, we are going with magnitude and normal to boundary. Click on apply, close. Now go to reference values. Reference values means our all calculation will be done with reference to these values only. Go to methods. We are going with simple scheme.
And we already discussed that why we are using the simple scheme in our introduction. Let's uh, recall that again, that we are using simple algorithm because here we are not using nth iteration instead of n plus 1th iteration, as results in linearization of linear convection term, decoupling of u and v equations, and it also helps to fix the direction of our upwind.
And for maximum accuracy and stability, we are going with second order upwind. And for transient formulation also we are going with second order implicit. After that, go to monitors, and in report files we will define the files which we want to plot or which we want values. Go to new,
Like all the values that we want to plot,
like
drag force, lift force,
go to new again, and force
force
report,
report,
drag. We will be calculating the drag force on geometry, so select geometry, and from here we can change the name. Drag force, print to console. Okay, okay. You can see that drag force file is listed here. Again we want the file of lift force, so go to new, again new, and force report, and lift here. Select geometry, change the name, lift force. Print to console. Print to console will print all the data values calculated in the console. Click OK. Okay. Now you can see that both the lift force and drag force file will be calculated. Close. Now we can initialize the. We are going with hybrid initialization. Hybrid initialization will give us more accurate value. So initialize. You can see that hybrid initialization is done. Now we will run the calculation. Go to run calculation. Define the number of time steps. Now let's take 80 time steps with time step size 1 second. And we are using time step size 1 second because for reporting file, they reporting file drag values come out after every 1 second. So we need to define 1 second. If you want to define step size different, you should be careful that it should value of time step size is greater than 1, because values are coming from report file after 1 second. So it will to make the graph, time step size should be greater than 1. Then defining the maximum number of iteration, let's take it 20 and run the calculation. Just hit the button calculate. It will calculate the all the drag coefficients, lift coefficients, and whatever value that we require.
It will plot it.
It may take some time based on your number of time steps and time step size.
Now we can also see that it is calculating it and plotting this graph. For now it is for lift coefficient.
Now we can see that calculation is complete. Click OK. For the given mesh size, this is our residual plot, which is always similar for every kind of simulation. We can see the drag coefficient is nearly constant, and the coefficient of lift is fluctuating. We will be discussing further in detail. So first let's plot the contour of velocity. Go to graphics, select contour, go to velocity, velocity magnitude. Select the whole, compute, save and display. You can see that we have this contour of velocity. You may also calculate stream function also. For now we are plotting velocity magnitude only, so close it. And if you want to show the vector direction also, we can go to vectors, select the whole geometry, velocity, compute, save and display. We can see that we are following direction of velocities. For better vision we can shift this left hand side. Now we can see that velocity plots direction are like this. You can also save the pictures in very clear format by going to camera option here, PNG format, save in any of the folder. Like for as now I am saving all the images on desktop only. Desktop, give to file name like vector velocity vector. It is saved now. We can see it on our desktop. Here is our velocity vector plot. You can also save the plots and all based on your needs. So till now we have seen how to make the geometry, how to mesh the geometry, and how to set up the things to get the simulation. And we have also seen the uh, velocity profiles of the fluid over the
And
geometry.
also we saw the lift force and drag force, those graphs, like how it is changing with time.
Now we are going to see the grid analysis. So for that, go to results. To do the grid analysis, we will choose a point in the planar body, and we will see velocity at that point for different mesh size, and we will see the graph of that.
And we are going to do it like multiple times to get the data for uh, multiple mesh size.
So now CFD post is opened. CFD post means post processing, means after the calculating the all the values what we want to find. So for that, go to location. We need to define the point in a plane. So first we will choose the plane. So select plane. You can give it to the name. I will not changing its name. Okay, and you can see that it is showing xy plane. You can change if your geometry is in different plane. We are choosing xy plane only because our geometry is in xy plane only, and z equals to 0 means normal. So just apply. So this is our plane, and we want to assign a point also. So we will take a point and 30 mm from the origin of the geometry. So for that also go to location, select point, okay, and from here we can see that it is in meter, so we will give it to 0.03. So you can see that this point is coming here. And now to calculate the values of velocity for this point, when node values, so when we divided, when we have chosen the number of division equals to 400. So for that, go to calculators, double click on function calculator. From here, now first we will calculate the area average of velocity uh, for all the plane. So select plane, from here select velocity and just click on the calculate. You can see that the average velocity over this plane is coming out to 0.35989, and we have our inlet velocity was 0.3. So just copy paste it and make a file like we have made in here. You can see that we have make the excel file of number of division, number of nodes, average velocity, maximum velocity, Reynolds number, lift coefficient and drag coefficient. For our initial number of division were 400, so for that average velocity is this, and we will choose the maximum velocity also. So go to that point again, select from here maximum value, select that point and velocity, again calculate. So maximum velocity is this at that point.
It is now almost 0.05 meter per second.
Control C and paste here, and we will also notice the number of nodes. So for that, go to workbench, open the mesh. Now you can see that mesh is open. So to check the number of nodes, go to mesh, go to statics. You can see that number of nodes is 21,350. So just copy it and paste it here. Now to make the new analysis for different mesh size, we need not to go for different geometry and again do the all setup mesh and all. We just go with this point, select this point and make it duplicate. So all the simulation will be duplicate to, it will make a copy of this simulation, and we will just change the number of mesh or number of nodes. So go to mesh, so you can see that our earlier geometry is present here and the earlier nodes and mesh is also here, but we need to change it. So go to mesh, go to edge sizing. We have used earlier 400 number of divisions, so let's calculate for 100 division and just generate. Now our meshing is done. For number of division equals to 100, you can see the number of nodes is different now. It is now 19,760. So again copy it and paste in our data. Go to workbench, go to setup. Before going to setup, just update the mesh. So now we will be setting the things for the new mesh. So start, and we will not do the all setup as we done in earlier part. We will just initialize the value for new mesh and we will calculate the values. So our new mesh is generated and we just need to initialize the mesh again. Initialize and run the calculation. You can see that all the value that we have defined earlier same is here. So now all the plots and drag coefficients will be calculated for new mesh, and we will select the maximum velocity and average velocity from here. So calculation is done. You can see that drag coefficient and lift coefficient also. So again, we will do post processing. For that, go to results, and similarly, we will calculate the values of maximum velocity and average velocity over the plane. For maximum velocity, we will calculate this velocity at that point which we have defined, and this time we need not to define the point again and the plane, as we have duplicated the similar simulation. You can see that the point is here only. So go, go to calculators, function calculator, select area average, in geometry select plane, variable velocity only, and calculate. Control C. This we have calculated for 100 number of division, and for maximum velocity again maximum value zero point 0.1 velocity and calculate. In this manner we can find the maximum velocity at a point and the average velocity over the plane for multiple times. We are taking it for 5 times to making the plot and to get the knowledge of grid independence.
So after doing the grid independence analysis, we are getting these values. Like for these number of divisions, we are getting these number of nodes, these number of average velocity on plane, and these number of maximum velocity of a point. Uh, so we are plotting these graphs. The first one is the average velocity versus the number of nodes. So here's the average velocity of whole domain, and these are the number of nodes. And like we can see that from almost 20,000 to 21,000 uh, number of nodes, the average velocity is almost constant, and it should be constant for this number. And after that we can see that it is decreasing. So the choice of our final mesh size should be between this range, like from 20,000 to 21,000. And then this graph is for the maximum velocity of the point versus the number of nodes. So we can check that this graph here. And now,
Now we will be discussing the effect of Reynolds number on lift and drag coefficient, and you can see similar to the way we have collected the data for this number of division, number of nodes, we can just go to the workbench, and after going to setup, we just need to change the initial conditions, not the entire domain. We will just change the initial conditions like velocities, and according to the velocity change, we will be getting different Reynolds number, and we will be getting different drag coefficient and lift coefficient. And from this graph we can see that drag coefficient is exponentially increasing while increasing Reynolds number, which is quite obvious, and the lift coefficient is fluctuating, that we have seen in our graph also. So it will nearly about zero.
So that's how we solved our problem of external flow problem for our 2D elliptical body. Thank you.
Thank you.